Our second speaker, Şener Özönder from Isting University. He will give a talk about physics and machine learning reunited. So, please, Şener.
Thank you very much. Hi, everyone. Thank you very much for invitation. My name is Şener Özönder. I am a faculty at Isting University in Istanbul at the Electrical and Electronics Department. So what I will talk about today is the connection and the long common history between physics and machine learning. So the aim of this talk is twofold. So this talk is for physicists and also for machine learning people. So first of all, we can describe machine learning in physics language so that physicists learn more about machine learning. We can talk about models of magnetism, which I will in this talk, renormalization group, partition function, and other ideas from statistical physics, how they are connected to machine learning. And we can also talk about physics foundations of machine learning. So physicists would be interested in this part. So how the ideas from physics, such as entropy, Callback-Liber divergence, restricted Boltzmann machines are used in the machine learning so that physicists can be interested in machine learning as well. So analogies and cross-pollination between the two disciplines, they have been happening for a long time. So we can explore these analogies a bit more, starting with this talk today, maybe. And concepts used in physics may also serve the artificial intelligence community. So let's get started. So how can physics help? There are some problems in machine learning. And I think physics and physicists can help to solve some of those problems. First of all, what we can do is we can draw connections between physics and machine learning and exploit those connections. In the following slides, I will talk about the relationship between statistical mechanics and the machine learning model, the two-layer neural network model, which is called restricted Boltzmann machines. They are definitely inspired by statistical physics. Or what we can do is we can also find maybe dualities between deep neural networks and some easy problems to reduce the cost of training deep neural networks. Some of these networks are trained by spending millions of dollars, just like the recent GPT-3, the natural language processing NLP model. So instead of spending those millions of dollars, maybe we can make dualities between neural networks and physics, easy physics problems that we know how to solve, and then we can help maybe AI community. How do dualities work? Physicists definitely know how they work. For example, you have a hard problem here. It may be a strongly coupled four-dimensional quantum field theory, which you cannot solve because there's strong coupling. What you can do is you can map the problem to a weakly coupled five-dimensional theory. It's gravity theory, and then solve it here, which is easy to solve here, and then you can map the solution back to the original problem. So we can maybe find dualities between machine learning, or in general, artificial intelligence and physics. So all of physics is about minimization or maximization of some objective function. So in this case, what we have is the Lagrangian is our objective function. The term objective function is often used by the machine learning practitioners. So it's the function that they want to minimize or maximize so that the neural network gets trained. So in our case, I mean, even the refraction of a light, it's a minimization problem. So what we have is usually Lagrangian, which includes the kinetic and potential terms, and we minimize it. We find the path of the particle or a light ray, whatever it is. Or in statistical mechanics, we have the free energy, and we try to minimize this to find the equilibrium point. And again, in statistical physics, we have Gibbs entropy. You can have the probabilities, and you can even have some constraints. In this case, the probabilities should add up to 1, or you can have another constraint for the energy, which I will show later. So these, depending on the entropy term that you have, it just looks like the Lagrangian. You can have microcanonical, canonical, or grand canonical ensembles. And this term is, by the way, if there's any machine learning practitioner, it just looks like Kullback-Leibler divergence. So also in chemistry, computational chemistry or computational physics, we still want to, again, minimize the energy. So we are looking for, let's say you want to calculate the energy states of benzene ring here. What you would do is you would run a DFT, density functional theory calculations, and what you would try to do is you would look for the electron density that would minimize the energy. So basically physics is all about minimization. And I will talk about minimization in machine learning later, but let's go with physics for a bit more. So most machine learning models, this is another problem that machine learning field has. They are black boxes. What it means is you train the network, the performance is 99.9, but it works well, but you don't know how it works. So that's a problem, especially if you want to apply that machine learning models in, let's say, in medicine. You want to know how the neural network works. So they're not explainable. So can we reach physics explainable AI? And as we know, explainability is the job of physicists. We see some data, we make some primitive models, and then we improve the models and we reach the explanation. So if there's one thing that physicists detest the most, I would say it's probably black box models. We don't like them. Machine learning models are highly susceptible to even noise. Let's say you train a model, and this is a duck, a picture of a duck, and so after you train the model, let's say if you show this image, it says it's a duck. Okay, that's good. But if you add even 7% of noise, it's pretty small, then the prediction of the machine learning model is this is a horse. So that's a problem. So they are highly susceptible to noise. Or you train a model that recognizes audio. Let's say you have the clip of audio, how are you? And you add 1% noise, and the machine learning model takes it as open the door. Or in this picture, you can see that if you have a picture or painting like this, you can easily fool the machine learning model. Okay, so the question that I want to arise here, can topology help solve the robustness problem of machine learning? 2016, Nobel Prize went to topology. So the basic idea of topology is they are robust to continuous deformations. For example, the topology here for these two objects is 0. The topological number for these ones is 1. The reason is that you can wrap some thread here or here. So there's basically just one hole. There are two holes here. One of the hole is here, the other is here. So what you do in condensed matter physics typically is let's say you want to calculate the whole conductivity, and you usually have a phase term. You take the integral, and the integral is always, this integral is always in multiples of integers. So the nice thing here is, so by the way, this is coming from the wave function in the system. But the nice thing is here, even if you deform the boundaries or the system, this quantity doesn't change. It's always integer. So, and the same here, you can deform this or this. So you can think of these as the deformed versions of each other, but the topological number or feature doesn't change. So, okay, so can we go beyond local pixel-based filter convolutions, that's what most machine learning models use when they are trained with image data. But can we go beyond them and can we use global topological features? One of the funny problems that machine learning models have is that they confuse Chihuahua and Muffin. So you can see that the machine learning, the performance is really bad in these cases. But maybe there is a way by using the ideas from topology, we can maybe cure this problem. Okay, so now I talked about a little bit machine learning now and also physics. Now let's move to condensed matter or solid state physics a little bit, and then we will make connections between these two fields. So some materials are magnetic below a critical temperature. If you cool down below TC, that TC may depend on the materials, and they become magnetic, they attract metals, and above that TC, they become non-magnetic. So the spin-spin interaction energy favors spin alignment. So the energy or the Hamiltonian is written like this. Of course, there's a sum here for each term, for each couple. So the energy, because of this negative sign here, the energy favors spin alignment because this is a lower energy state. But what heat does, it randomizes the spins. So that's the entropy, and it favors random spin orientation. So there's a trade-off between energy minimization and entropy maximization. And you know that free energy is average energy minus TS. Okay, so material becomes magnetic below TC. So there's an average spin below TC. This is average spin. You can think of it as magnetization as well. So it's non-zero below TC. And right at TC, there is a phase transition. So above TC, you have just random spins like these. These particles here simulate the temperature, the ambient temperature. So they hit these spins, they randomize them, so they create entropy. So above TC, well, the average is basically zero. But as you go below TC, so if you're far away from TC, below TC, then you get non-zero magnetization because most of the spins now, the temperature effect, the effect of these guys, they would create entropy and randomization. So they are low at low TC. So you would get an ordered state with net magnetization. And if you go to zero temperature, you get magnetization or average spin to be 1. So there's a phase transition at TC. Okay, so spin wants to align to minimize the average energy. And if you write down the Hamiltonian for this setup, for example, so the spins are, all neighbors, the spins are in opposite directions. So you would get -1 from each bond. So you would get ultimately 4. In this case, the Hamiltonian is our energy in units, 4 units of energy. Now, but the ambient heat or temperature wants to randomize the spin directions. Now, this is quantified by the entropy term. So in this setup, if you insist on this energy, that energy is 4, then there are 2 possibilities. And the entropy is basically log of multiplicity of states, which is, in this case, log 2. Now, free energy it becomes minimum when the thermal equilibrium is reached. Free energy is analogous to the objective function in machine learning, such as Kullback-Leibler divergence. So when the free energy is minimized, the final spin positions, so some of the spins are up and some down, so they are analogous to the weights learned in artificial neural networks. So if you train a neural network, this is the input layer, this is the output layer. So you feed the network with a bunch of data, and when it learns, what it learns is basically the weights between the nodes. So when you have these numbers, then you can say the network is trained. Now you can use that network to make predictions. So, but we are not interested in the states of spins at the individual level, right? I don't really care about if this spin of this spin is up or down. Or in the neural networks, I don't really care about the particular or individual weights. What I care about, the observables, which are macroscopic variables like magnetization, just spin average, temperature, energy, etc. In the context of neural networks, the corresponding variables may be output layer as the weighted average of hidden layers. So here we calculate the we take an average of spins. It's a simple average, just arithmetic average. In this case, you do this, you do similar thing, but you average over these weights. So what you're interested in here is basically the output layer, not the individual weights. So how does magnetization change with temperature? Let's talk about this. So this is the free energy, and this is the average magnetization, or the average of spins. So if a spin is up, then you can think of it as 1, down is -1. If you are at high temperature, let's say 2.4, TC happens around 2.2, 2.3. So you're above the TC, your free energy is something like this. So the minimum of this free energy at this temperature is this point. That means the spin average or magnetization is 0. And what happens if you go to colder temperatures? Let's say you go below TC, let's take this one. Now your free energy is like this. So you are either here or here at one of these minimums. So this minimum is like all the spins are down, and this minimum is for all the spins up. So the point here is that thermal equilibrium free energy is minimized. Okay, so let's slowly go into the ideas of entropy information, and they will be useful for the following slides. So here we have it. So again, think about blacks as down and white cells are up. So you can think of +1, -1. So at high temperature, what you have is the free energy. So this is high temperature, completely disordered. So the average magnetization is 0. So here we are at high temperature. It's disordered, random, untrained. So this is a term from machine learning, and the average is 0. The information here is incompressible. I cannot really compress this information. I have to keep it like this. This is a noise. You cannot compress noise. Complete ignorance, because information is not it's not compressible. So each spin can be up or down. There's a complete ignorance here. So the entropy is, you can calculate entropy for each spin case, and you find log 2. So this is a high entropy state, high information content. Now, if you go to low temperature, below TC, what happens is you are one of these minima. So here we have almost all spins down, but there are a couple white ones, so you can think of them as up, but the magnetization is -1 or almost -1. This is a low temperature state. This is ordered, trained, and the average is -1. Information here is incompressible. If I want to talk to you about this state, I can say it's black and there are a couple whites, and you can actually calculate entropy here. It will be lower entropy, because there are only so many points that you can place these white dots. Here there are just too many points, but here is less points. So there's complete knowledge. Each spin is down if, well, this happens at t equals 0, definitely. And at t equals 0, the entropy is 0. That's a low entropy state, low information content. Okay, so let's talk about traveling salesman problem. So, and I will say that learning in machine learning or any algorithm, it's actually cooling. So the idea here is there's a salesman, he has to go to different states, sell different certain products. So what is the shortest path for him? So you run a simulation. So basically you're trying to learn the optimum path, and in this case learning is cooling down because you simulate this by using a fictitious temperature. It's not real temperature, but you call it temperature. Temperature is decreased with small steps to reach the minimum of the cost function. And you define it, you define the cost function as the minimum distance, or the distance. When it's minimized, then you get the minimum distance. So it's the total tour distance. And learning rate here, which is again a term from neural networks, it's the step size here at temperature. And you can see here that there's a temperature. It goes down. Again, this is a fictitious temperature. It goes down with iterations. So the system learns, and as the system learns, the distance, the tour distance goes down. So this is the point where the algorithm learns. Okay, so Ising model, we talked about it. It's not very interesting because the free energy minimum corresponds to all spins up or all spins down. So all spins up or all spins down when it learned or when it goes to the ground state. This is not interesting. So what's interesting is, and oftentimes people make connections between machine learning and the model, Springglass models. These Springglasses are, they happen in various materials such as silicon oxide. So Springglass model, it has a richer structure. The minimum energy states correspond to rich spin configurations. So now here, Jij is the interactions between spins are not the same. Here they were the same. So J was equal to 1 here, but here those connections or interactions are different. So for each spin, I have a Jij in the Hamiltonian. So when this system cools down, when you find the ground state energy, it's not like Ising model. So you can have spins in different directions. Now, the learning here is basically what you learn in this model is the directions of each spin, and it corresponds to the weights learned in the neural network. And if you look at the free energy of the Springglass model, the ground state is interesting. The ground state doesn't have just like 2 minima, it has multiple minima. And I will talk about how this is relevant to machine learning, probably in this slide. So the question is why deep learning doesn't get stuck to a local minima during training. Why does it find the minimum so effectively? Deep learning models are so effective. So the reason is that there are billions of weight parameters. So here, of course, you see just 2 hidden layers, but usually there are thousands of layers, millions of nodes. And so there are billions of weight parameters in a deep neural network. So flat directions or saddles are abundant in 1,000-dimensional loss space. So even if you are, even if you, let's say you cool down, you train the network, you stuck in this local minima, but there's always another direction that you can continue. So of course, if you do a training in 1-dimensional, there's a possibility that you will get stuck here. But if there are multiple dimensions, you can always go those directions and continue to find the ground state. So this is the reason why deep neural networks work so well, because they have millions of parameters. Okay, so let me talk about restricted Boltzmann machines. So probability of a specific configuration at temperature T is given by the Boltzmann distribution. We know this from statistical physics, where the energy in this case is given by the spin pairs. So this is the most likely configuration at low temperature, and this configuration is most likely at high temperature. So here, this probability, it comes from the maximization of Gibbs entropy. You maximize it with the constraint that all the probabilities should add up to 1, and also there's a constraint, another constraint, where we can define average energy. So when you do the minimization here, you end up with the Boltzmann distribution. Now, restricted Boltzmann machines, it's a generative neural network architecture. They are similar to Springglass models because RBMs, restricted Boltzmann machines, accept only binary inputs, so spin up or spin down, +1, -1. But the weights can be anything. These weights can be anything. Since RBMs are energy-based, Boltzmann distribution between the visible and hidden nodes arises naturally. So because these are energy-based models, we get Boltzmann distribution naturally. If I go back to the slide, the reason that you get, again, the Boltzmann distribution is that you can define energy. The same thing happens in these models. There's just two layers. So what happens is you have a bunch of people rate these movies, Lord of the Rings, Matrix, Fight Club, Harry Potter, Titanic, Hobbit. So people rate these, they like, they dislike, okay? So what this network does is, just based on the ratings, plus or minus one, it basically classifies these movies into drama, fantasy, and science fiction. So the probability distribution here is the Boltzmann distribution. It's basically, it gives you, let's say someone, so you train the network and then someone comes, makes this rating for these movies. So this probability distribution tells us that given the rating, this rating, what is the probability that the person likes fantasy or, let's say, drama genre. So these networks, so you can see the connection between the machine learning and physics here. Now, let's move to autoencoders. So unsupervised learning method of autoencoders are useful for finding latent variables. 3 minutes, okay. Okay, thank you very much. So you can train the autoencoder. It's a neural network with real faces. And so the way that you train autoencoders is the input and the output are the same. And then what you look at the hidden layers, and they give you eigenfaces. So what are the fundamental or the basic building blocks of these faces? So it basically gives you eigenfaces. So step one, train the autoencoder, learn the main features of the data, encoded in the hidden layer in the middle, which is middle layer. So, and then you can, if you want, you can use this model as a fake image generator. So you take this part of the model, you provide some random noise here, and it generates fake images. These people never existed. They're just fake images created by the generator. So now with my student, we were wondering if we can use it, apply it to Ising model. So we simulated the Ising model at finite temperature with Monte Carlo. So we took samples 4x4 Ising configurations for different temperatures, and then we so this is 40 by 40. We flattened them to vectors 1/1600. And then we trained these configurations. We trained this autoencoder with these configurations by using the configurations in the input and output layer. And then we looked at the hidden layers. Now, here's the result. When you look at the hidden layer, hidden node, the second hidden node, its value jumps at, this is the temperature, at 223 at this point. So the exact solution of Ising model gives phase transition, so at 227. And this is the exact result, and our network finds the critical temperature at you can compare them, it's 2% error. This is pretty amazing. So autoencoder here was only fed the Ising configurations, not their associated temperatures. So we don't give it the temperatures. We know which configuration corresponds to which temperature, but we don't give the system, the autoencoder, the temperatures, but it can find basically the phase transition point in two-dimensional Ising model. So let me finish with two more slides. So convolutional neural networks are used for image recognition. So you basically have filters and activation and pooling. Pooling is, it's a coarse graining, it's zooming out or downsampling, integrating out fine details and leaving out the large-scale structure. There are different poolings, max pooling, average pooling. In fact, we do this in when we do block spin in physics. So max pooling is basically take the maximum number, average pooling is basically take the average. So in physics, this is related to renormalization group. It's used to discover the scaling laws, power laws that quantifies quantities like specific heat, correlation length, and magnetic susceptibility. So the change of free energy by averaging or pooling. Spins tells us how thermodynamic variables change at temperature close to the critical temperature. Here you can do the block spins, and you can run the renormalization group procedure here. And finally, let me flash this slide. If there are parties interested in the connections between machine learning and physics, they can look at these books and reviews. So thank you very much for giving me this opportunity, and thank you, I thank the organizers.
Thank you very much for a nice presentation, Şener. Is there any questions? So I can ask one more question, Şener. Did you look at next neighborhood in the Ising model?
In this case, no. It was just next neighbors. We haven't looked at NN neighbors, so that can be done, and I think that would give you again the problem. My guess is again the phase transition, shifted phase transitions in that case as well.
Thank you. From Sergey, thank you very much. Very nice, interesting talk, he said. So,
thank you, Sergey.